now that we have a semi-perfect definition of a system, we're going to start jumping in straight in with mechanical systems. So system dynamics, we're very comfortable with mechanical systems. I don't know why dynamics is not a prerequisite for this course. I think because most times, especially by the time it shows up in the schedule, it's assumed that students would have taken dynamics. I have had students who've taken dynamics before. While they're taking systems, I would not recommend it. Talk to your advisor, talk to me if you're in that situation. But we have mechanical systems. So if we look here, we're going to have a mass spring damper system. Oh, and I didn't do this in the fancy way. Let's do this the fancy way. What's the fun with cool technology if we don't make use of it? So let's think about if we have a speaker, a car suspension system, an aircraft wing. All of these things are going to be able to be represented with a mass spring damper system. And earlier we said that a system is going to be a collection of components that interact with one another. So in this case, we have the mass, the spring, and the damper are easily identified through title alone as the components. And we want to be able to map inputs to outputs. So if we have our mass spring damper system, our inputs might be the force that we apply upon it, so F of t, or our initial conditions. What's our initial velocity and our initial velocity or our initial position. And our outputs would be our position or our velocity, or we could do acceleration, or we could do the second derivative at any point. If we have x of t, we can find all of those things. So what we want to find is how is position a function of the input force and our initial conditions, starting position and starting velocity. Because once we have that, then we could figure out anything that's going on with the system based off of those initial conditions and any input forces. And when we go through any type of system in this class, we're going to be identifying a couple of different steps. So first thing we want to do is we want to talk about what are the inputs and outputs of our system. We know that now. Our inputs are going to be force and initial conditions. Our outputs are going to be our position at any time. The next step is going to be to use our knowledge of physics and engineering to observe the mathematical connection between the inputs and outputs. And then what we're going to do is, once we have some sort of mathematical structure, then we can simplify it in order to be able to predict the output for any input. So we can model any type of system. And so, as I said before, we're going to have that we've identified our inputs and outputs, and now we want to see what's the next step. So, for each time that we talk about a system, we're going to start off by looking at the governing rules. So, this is a physical system, we're using mechanical systems, and let's go over some of our equations. I'm going to speed this up a little bit because then it looks cooler. And again, these videos are just supposed to be a review and not in lieu of class. So, wait, hold your horses. So, start off with, we might have the sum of our moments, and the sum of our forces is going to affect the acceleration. So sum of our moments is equal to our mass times acceleration. Sum of our forces is equal to our mass times acceleration. Sum of our moments is going to be equal to our mass moment of inertia, our mass, I am still dealing with a lot of sleep loss due to having an infant baby. So if you're taking this course and I'm an old lady, then that means I've filmed these a long time ago. So, our mass moment of inertia times our angular acceleration. There we go. Then we are going to have several different elements that we can interact with. So in this case, we have springs and dampers. So the force of a spring is going to be equal to the spring constant times the displacement. So here I have that the displacement is x minus x naught, and x naught is not the initial value of our displacement, but it's rather what's the equilibrium point, or if we set it x naught to be measured from the equilibrium or measured from the unstretched spring, then that's going to allow us to just say that x minus x0, we can just say that's going to be 0 if the spring is unstretched. It makes our math a lot easier, because then our spring force will just be equal to K times X. Our damper, we're going to simplify as saying that it's equal to a constant, our damping constant, times our velocity, x dot. And we want to figure out what's going on. We're going to draw a free body diagram. So we have our spring force, our damper force, and we always have that the spring and damper oppose motion. So if X is going in one way, then we have that our spring force goes the opposite direction, damper force goes opposite, because that's what springs and dampers do, they oppose motion. So we have that the sum of our forces is equal to mass times acceleration. So here in this case, F of t minus, this is too fast for comfort. So this is nice, oh, I should use those buttons. There we go. F of t minus our damping force, c x dot, minus our spring force, kx, is equal to our mass times acceleration. We can rearrange those to get a differential equation. So we've completed step 2, where we use our knowledge of physics and engineering to observe the mathematical connection between inputs and outputs. For these videos, I expect that if you are taking this instead of class, it's up to you to be able to pause, take the notes so that you would see the analysis of the system in front of you. If you're just doing it to review your notes, then you should have those notes in front of you. So I'm not always going to refresh what you've seen, because that's not the point of these videos. It's just supposed to be a refresher rather than you learning from start. So in this case, we can look at our output is going to be our x double dot. We can think of it as an output, or we can say x of t or x. And our inputs are going to be that force and our force, our damping force, our initial velocity values. This is not right. Okay, let's go ahead, press pause. Okay, we're going to say that our inputs are going to be our initial position, our initial velocity, and that force that we've applied. Our output is x of t. Now, in order to turn this equation that we have here from our free body diagram into some x of t is equal to a function, we're going to need to solve this differential equation. So the next video is going to be talking about Laplace transforms, because that's going to be the tool that we use to start to solve these differential equations.